Hello, everyone. My name is Matthew Ferry. I'm here to host our Climate Action Tech for this evening. So this is our Western Cat Salon, where we've got Thomas joining us to talk about sustainability in buildings and how we can make the energy transformation. Climate Action Tech, if you're not familiar, is a community of tech professionals with the goal to inspire and empower each other to take climate action. And we run this call to share ideas and facilitate conversation within our community. We run it both in Western and Eastern friendly time zones. And this is our Western friendly time zone. So with that, I wanted to hand you over to Thomas. Thomas is a fantastic software engineer with an entrepreneurial attitude, and he's come to us with an interesting problem focused on how we can think about sustainability and the energy transformation for our built environment. So Thomas, over to you.
Thank you, Matt. Let me share my screen. So yes, thank you so much for being here. My name is Thomas Alisi, and I'm presenting the results of this project called Energy Open Piazza that has received funding from BEIS, which is the Business, Energy and Industrial Strategy at the UK government, and Natural Resources Canada. So it's been quite a long 15 months long project. We are now coming to the end of the funding, and we're figuring out how to scale it, how to make it a commercial proposal out of it. So let's start with some knowledge about what's happening and framing the context of this project. So we know that we are witnessing climate change at a big scale. We have the net zero target by 2050 as a goal that we are all seeing every day, always closer. But there are some things that are not immediately evident, like, for example, we are expecting in the same period about an 8-fold increase in energy consumption. This is the scenario proposed by Bloomberg NEF. And this is due mainly to electrification of heat and transport, which will be a big source of energy consumption. Interestingly enough, the built environment, and I'll define what built environment means in a minute. The built environment represents roughly 30% of the global emissions worldwide. With built environment, we intend basically everything that is buildings related. And with building operations, we intend whatever is needed to run the building in the whole life cycle of the building itself. So the study 30% global emission was by the International Energy Agency and GEBC, which is the Global Alliance for Buildings and Constructions. Now, the UK, I don't know if you guys have seen the energy white paper that has been published by the UK government in December 2020. It makes some really serious commitments on how we're going to reach the 2050 net zero target. One of the ones that are most interesting to us is that all UK non-residential buildings will have to be certified EPC energy performance certificate by Band B by 2030. What EPC means is that it's a set of kind of static metrics that are based on the characteristics of the building, such as the type of insulation, the type of lighting, and the window glazing, and these kind of things. So this is really good news, but we see a problem in it. So the problem that we see is that EPCs are a little bit too simplistic and a little bit too static to address the problem of net zero, because they don't consider, for example, that the grid is changing, that is progressively switching to renewable energy, that the consumption is growing. So net zero as a problem, we think that it has implications on behavioral change, on how we actually use the electricity. So EPC is a first step toward net zero, but we need to do more. And to do more means that there's plenty of money that we'll need to spend in the forthcoming 30 years to optimize and to better the infrastructure, to make it more resilient, to make it smarter. So our idea was that we need to somehow deploy an infrastructure that is expensive. Why don't we have a look at how we spend that money so that we are sure that we're spending that money in the right way? Because in our vision, we we see a future of hybrid buildings. We call them hybrid buildings. They are not passive consumers as they've been so far, but they're what they're called DER, so distributed energy resources, that are something more active, that balance or actively participate in the grid. Now, if we think of a building as an active player in the grid, and we need to think of this at scale, like hundreds of thousands, if not millions of buildings across the continent, we need to be able to optimize them in real time. And that needs a very sophisticated network of digital tools that are able to interact with each other. So this basically introduces the concept of a digital twin that basically is something that simulates the behavior and forecast the consumption and generation of any distributed energy resources, any DER in the network, and then possibly verifies that the model is actually matching what the forecasted consumption and generation is. Not to mention that if we were to implement this sophisticated distributed energy resources grid, this could potentially change the commercial real estate industry at large, because basically it changes a lot of the metrics and KPIs that the real estate industry is based upon. So what we have done, we have received funding from BEIS and Natural Resources Canada. Our goal is to build a platform that understands the deployment of energy solutions. So energy solution, we started with, have to say, we started with, it's a massive problem. We started looking at a subset of the problem, which is the deployment of solar array, PVs, and energy storage. So we built this platform that makes a forecast and assesses if the investment in PV and storage is sensible or not, whether that would be from the point of view of the economic sustainability or the carbon emission reduction. So we have implemented research. We have a consortium with other organizations, amazing organization. We have implemented research from UCL and Sheffield. We have University of Sheffield. We have validated the models with Energy Systems Catapult. And the idea is that we want to see whether it's doable to implement and deploy these assets at scale, energy assets at scale, and basically try to find the balance between economic feasibility and the reduction of carbon emissions. So I'll give you a quick demo of what the platform does, or at this stage. I've recorded this video. It's just 2 minutes long, and I'll talk over the video. Can you guys see the video now? My screen? Yeah, okay, cool. So what it does, we onboard the building by entering the address of the building or the name of the building. then we create a simulation of what the load consumption would look like by entering the total amount of kilowatt hours consumed. Then we pull the content from maps. If the building is not readily available, we can draw a map of the building and define the main parameters of the building. And then basically once we are ready, we say, okay, generate the simulation for this building. You can also upload the smart energy data if they're available. Then the platform goes through a quick walkthrough to show what the interface does. Once we're in, we can start with the asset configuration. So we have a building and we set the energy transformation that we want to create for that building. The system generates an initial recommendation of a battery storage and a solar PV array. Then you can tweak the parameters, very simple, basic parameters, but you can dig down a level deeper and go into the fine details of the buildings, where you can start like breaking it down in terms of how, in this case, the roof is built, what type of ventilation, what glazing of the windows, what's the ratio between wall and windows. So it basically refines that view of the building so that it gets to a point where it has a good understanding of what the best recommendation would be, and then it generates a business case. And the business case basically is looking at the optimal energy dispatch of the PV and storage production to understand what the savings are in terms of both savings, economic savings, and carbon emission reductions. So, oops, sorry, I'll go back to my presentation here. So now that you have a better idea of what the platform does, I'll give you a little more insights, but not too technical, on how the platform works and what is actually the data that we have to analyze. So this is basically the path that we follow through the whole onboarding, from onboarding to down to the business case generation. So we do the building onboarding, we create a load simulation, we look at the building features. If the user has the smart meter readings, then that is used as well to create a view of what the building is. And then we run the recommender that says, oh, okay, based on this consumption, you'll probably be looking at some size of battery and solar generation. Then we run the simulation of the solar generation. And then we have implemented our models for the carbon intensity for the grid with a half-hourly resolution for the UK and Canada. And then basically putting everything together, we run the energy dispatch and we say, okay, we change the state of charge of the battery. Basically, we charge and discharge the battery, and we see what is the best solution for both the pricing and the carbon intensity in any 24-hour interval to optimize how the energy should flow. And that allows us to build us the business model. So what have we done in terms of making the recommendation? Basically, we are looking at the problem holistically. we're trying to do data-driven optimization. Basically, this is the part that we trigger at the beginning, where we say, when we look at the data and we say, okay, you'll probably be able to optimize on a set of parameters. Where we start from is an analysis of the load and temperature ratio. In this case, for example, you see that when the outdoors temperature goes up, you have also the consumption going up, and this is possibly an indication that there's a potential for optimization for the ventilation system, because higher consumption means that probably the ventilation there can be optimized. Which is a little bit generic, but we do further observations on whether the heating or cooling are wasting energy. And what we do is to have a look at the different periods of the year with similar temperatures, but potentially different load consumption. So what happens is that if we see that outside temperature are similar, but the consumption is different, it probably indicates that the building is running somehow on autopilot, and it says from June to whatever, end of August, you need to run the HVAC at this power. But that doesn't reflect the reality of different days that might offer some spaces for optimization. So looking at that data, we say, okay, you probably have those margins that you can potentially be used. Instead of sucking energy from the grid, you can use it for something else. For example, for your EV charging infrastructure, or for other uses that might be like useful for the building infrastructure itself. And then once we have all this data, we create the digital twin of the battery. And what you see here is that the blue line is the load of the building. In this case, is real data of a real building, so data coming from a smart meter reading. The red line is solar generation for a digital twin. So basically create a simulation of solar generation for that building, considering the footprint of the building itself. And then what it does is, like, you see that the yellow line, it goes up and down, and basically it's trying to optimize on energy pricing and carbon intensity of the grid. So basically it's trying to arbitrage on the opportunities, both of carbon and pricing. So what are these opportunities exactly? Opportunities are, in our cases, are the pricing and the carbon intensity. So these are exactly the same intervals as before. You see here the blue line is the carbon intensity of the grid, which is expressed in gram of CO2 per kilowatt hour. So you see that it can vary quite wildly from 100 grams to 400. This is the UK. In Canada, Alberta can be extremely high, a lot higher than the UK, while in Ontario, which is mainly powered by hydropower, that would be a lot lower. And then you see the red line, which is the energy pricing at wholesale price. And this is in pounds per megawatt hour. And you see that there's some correlation at points. So when, not always, but there might be some delays, but there's definitely some correlation between the peaks in carbon intensity and the peaks in electricity sale price. And that's because Sometimes they need to switch on and off the backups and do the adjustment to the grids to make it run smoothly. Just to mention something that happened in February, if you remember what happened in Texas when they had that big storm that created a lot of problems to the grid, and the gas pipes were frozen and they had massive problems in distribution. You had the wholesale price of energy that shoot up in almost 24 hours on the 20th of February from $50 per megawatt hour to up to $9,000. So we're going to see a lot more of this. So the potential for arbitraging on both cost and carbon intensity is potentially increasing a lot in the coming year. The output of the platform is this is kind of a sample output of the platform on a real building that has been anonymized. You see that once basically this is the result that is then printed in that business model page once the analysis has run on this consumption. In this case, you have 3 million kilowatt hour of consumption, which is around 420,000 pounds, and an average yearly carbon intensity of 600,000 kilograms of CO2. With the transformation, so we make it a digital twin of the transformation, and we say roughly at the 330,000 pounds transformation, 350 kilowatt peak solar panels, and the 230 kilowatt lithium-ion battery, then the yearly energy savings would be roughly 110,000 pounds and 60 tons. So the numbers are looking good because you have a payback time of 5 years roughly. But it's not happening. So this is pretty much the discussion that I would like to have, that I have had plenty of times with all sorts of stakeholders. We have a building stock in the UK of 1 million building, non-residential, 1 million building that will need to be EPC Band B by 2030. It's a lot of buildings, and you would expect them to be transformed at a very, very fast rate in terms of a few tens of thousands a year, but this is not happening. What we're trying to understand here is something obvious that we're missing, or something obvious that is broken, like what are the commercial and commercial real estate KPIs? What is the driving force for the KPIs of the commercial real estate? Or do we need a marketplace, or do we need reporting for transformation? So something, I don't know, something that it should be there, but it's not. Who are the decision makers for this transformation? I have been in countless meetings talking to people saying, no, I'm not the one. We need to add, and we need to call another person. And you have these meetings that get bigger and bigger, and then the decision is not taken. But there's also some other problems of potentially involving the management company or the planning or engineering company. Is the energy the best side to approach the emission problem? Like what I was saying earlier on, shouldn't we just go and plant a lot of trees, or try to find a better way of creating, I don't know, green cement or other technologies, rather than making the super techie solution for the buildings? Do we have the right technologies? Like, is it mature enough what we're doing? Are we considering the whole set of problems, like the life cycle of lithium-ion batteries or EV charging infrastructure and so on and so forth? So are we there, or do we need to wait a bit of time? And finally, do we have the right regulations? Like what do we need for this to happen, if at all? Subsidies or carbon tax or the smart export guarantee, which is the latest way of making solar panels being participating to the grid power. So this is I normally end this presentation with not with a question mark, but with an assertion, which is it's time for hybrid buildings. But now I'm somehow reverting the question: is it time for hybrid buildings? And this is something that I would like to discuss with you.
Amazing. Thank you so much for your presentation, Thomas. I think we're all excited to follow on with that discussion. If anybody is watching this on YouTube as part of the recording, please join the Climate Action Tech Slack space so that you can follow along with these sorts of discussions in the future.